Chapter 5, Cold Water Systems, Part 8. The components used in boosted pumped cold water supply systems from private water sources. The components used in boosted pumped cold water supply systems from private sources for single occupancy dwellings. In this, the final part of the unit, dealing with the private water supplies, we will investigate the components used with private water supplies to single domestic dwellings. Number 1, small booster pump sets with small booster pump sets which incorporate all controls and components. Number 2, boosted systems which separate controls and components. Number 3, use of accumulators in increasing system flow rate. Vertical, horizontal, and submersible pumps. There are 2 different types of pump that can be used with private water supplies, more specifically boreholes and springs. Number 1, surface pumps such as horizontal single-stage pumps, vertical multi-stage pumps. Number 2, submersible pumps. Surface pumps for private water supplies are available either as single components or as packaged units containing all the necessary equipment pre-fitted. The latter are the easiest to install and require only the final plumbing and electrical connections. Submersible pumps may be purchased as separate components or in packs with all the separately matched equipment supplied together ready to assemble. A typical pump package would normally consist of the following components: the pump, the transducer to sense pressure and flow, a control box to monitor pressure differentials and flow rate, an accumulator to assist in providing sufficient system pressure for the installation, a float switch to prevent the pumps running dry. The accumulator. The accumulator is a pressurized vessel that holds a small amount of water for distribution within the installation. It is designed to maintain mains operating pressure when the pump is not working and to reduce pump usage. Small accumulators can also be used to suppress water hammer. Small domestic installations use bladder-type accumulators. These consist of a synthetic rubber bladder or a bag within the coated steel cylinder or a vessel. The operation of an accumulator can be broken down into 3 stages as follows. Number 1, when the pump operates, it forces water into the accumulator bladder, compressing the air surrounding it to a pressure greater than the vessel's pre-charge pressure. This is the source of the stored energy. Number 2, when the bladder expands due to the water being forced in by the pump, it deforms in shape and the pressure within the accumulator increases. Bladder deformation stops when the water and the now compressed air charge become balanced. Number 3, when a tap is opened, the pressure within the system drops and the compressed air forces the water out of the accumulator. When all of the water inside the accumulator is used and the pressure falls to a predetermined level, the pump energizes to recharge the accumulator water storage and pressure, and the cycle begins again. Probably the most important consideration when applying an accumulator is calculating the correct pre-charge pressure. The following points must be considered: the type of accumulator being used, the work to be done, the system operating limits. Improve your maths. Pre-charge pressure is usually 80 to 90% of the minimum system cut-in pressure, the pressure at which the pump energizes, to allow a small amount of water to remain in the vessel at all times. This prevents the bladder from collapsing totally. To calculate the pre-charge pressure flow, follow this simple procedure. To calculate the pre-charge pressure, follow this simple procedure. If the minimum working pressure of cold water system is 2 bar, then 2 times 0.9 or 90% equals 1.8 bar. Pre-charge pressure equals 1.8 bar. The accumulator air charge must be lower than the mains pressure for water to enter the vessel, and on average a pressure differential of about 1.5 bar lower than the supply pressure would be acceptable, but no more than 2 bar and no less than 0.8 bar. This means that if the supply pressure is 3.5 bar, then the air charge within the accumulator must be around 2 bar. A supply pressure of 4.5 bar would require a 3 bar air charge, and so on. Air pressure can be checked and topped up as necessary at the Schrader valve, a tire valve where you put the air in, situated at the top of the accumulator. Float switches, transducers, and temperature sensors. Float switches, transducers, temperature sensors. Float switches, transducers, and temperature sensors play a vital part in the modern, boosted, large-scale cold water systems. The problems encountered are not just those of how to install them, but also where to install them. Installations of large systems are often undertaken in tight and restricted spaces. Difficulties arise in positioning these components while providing access for maintenance and inspection. Here, we will look at these important components. Float switches. Float switches, often called level switches, provide detection of water levels within the system to activate various other pieces of remote equipment, such as start-stop functions on boosting pumps, open-close functions on solenoid valves, water level alarms, and water level indicators. There are many different types of float switch available, and these can vary in sophistication from simple magnetic toggle switches to ultrasonic and electronic types. Popular types include magnetic toggle, a simple float switch that uses the opposing forces of magnets to activate a micro switch. Sealed float switch, sealed float, pressure activated diaphragm, electronic, ultrasonic. Transducers. A transducer is an electronic sensor that converts a signal from one form to another. In large-scale multi-story water systems, it sends system pressure variations and converts a preset low pressure into voltage to activate either the boosting pumps or the compressor feeding the pressure vessel to boost the pressure to normal operating pressure. Transducers may also be used to sense overpressurization. Temperature sensors. Temperature sensors are often used to monitor the temperature of large volumes of water stored, wholesome, potable water where the installation is of a major importance, such as in a hospital, prison, or any place where there is a duty of care. Key term, duty of care in the British law, the moral and legal obligation imposed on an organisation or individual which necessitates that a standard of reasonable care is adhered to. If the standard of care is not met, then the acts are considered to be negligent and damages may be claimed for in a court of law. Temperature sensors. Temperature sensors are often used to monitor the temperature of large volumes of stored wholesome potable water where the installation is of major importance, such as in a hospital, prison, or any place where there is a duty of care. The water supply, water fittings regulations advise that stored wholesome water should not exceed 20 degrees Celsius in order to minimize the risk of microbacterial growth. Cold water storage systems. Storage systems and the water regulations. Schedule 2, paragraph 16 of the water regulations tells us that a storage system supplying low pressure cold water supply to sanitary appliances or feeding a hot water storage system should be capable of supplying potable wholesome water. Various protection measures must therefore be included in the design of the system to ensure the water supply does not become contaminated or unwholesome. To comply with the water regulation systems must be fitted with an effective inlet control device to maintain the correct water level, i.e. a float-operated valve. Be fitted with a service valve on inlet and outlet pipework connections. Be fitted with screened warning overflow pipes. Be covered with a rigid close-fitted lid which is not airtight but excludes light and insects. Be insulated against freezing or undue warming. Be insulated so that the risk of contamination is minimized. Be arranged so that the water can circulate, preventing stagnation. Be supported to avoid distortion or damage that could lead to leaks. Be readily accessible for maintenance and cleaning. Systems must be installed to these requirements if the problems of contamination are to be avoided. In the past, when systems were fitted with unscreened overflows and poorly fitting lids, insects and small mammals could easily gain access to the water the systems contained. Some insects, like mosquito larvae, need water to complete their life cycle, and these must be avoided. Schedule 2, paragraph 16, therefore, sets out to prevent this, both in the manufacture and the installation of the system. Correct installation will, in most cases, eliminate the problems mentioned, especially when avoiding the problem of stagnation of water. Types of domestic system up to 1,000 litres. Types of domestic system up to 1,000 litres. Storage system. This is designed to hold a supply of cold water to feed appliances fitted to the system. On indirect cold water systems, storage systems are used. It supplies cold water only. Feed system. This can be identical to the storage system, however, it holds only the water required to supply the hot water storage vessel. In other words, it supplies cold water to a hot water storage system. Combined storage and feed system. This is a combination of the previous two examples It is used in an indirect system of cold water where only drinking supply is taken direct from the main and the rest of the water is supplied from a cistern. It stores water from the domestic hot water system uh, for, for the domestic hot water system, and the indirect system of cold water to the appliances, wash, hand basin, bath, WC, washing machine, etc. Feed and expansion system. Used to feed a vented central heated system also allows expansion of water into the cistern when the system is hot. WC and automatic urinal flushing systems. Used to clear the contents of WC or urinal. The water they contain is not considered wholesome. They will be covered in more detail in Chapter 9, Sanitation Systems. Capacities of domestic cisterns. The British standards no longer make reference to the minimum requirement as to the amount of water that is stored in a cold water cistern. Instead, BS-EN 806 and BS 8558 recommend that each dwelling be taken separately and the amount of water calculated to suit the needs of the dwelling and its occupants. Kitchen sinks cannot be supplied from a protected cistern. Their supply must come direct from the mains cold water supply. General installation requirements for domestic cisterns. Water is heavy. At 4 degrees Celsius, it weighs 1 kilogram per litre, so 230 litres will weigh 230 kilograms, almost a quarter of a ton. From this, we can appreciate that a cistern full of water will need adequate support, especially if placed in a roof space. Normal practice would be to try to place the cistern over a load-bearing supporting wall, as shown in figure 5.44. But if this is not possible, then the platform or stillage must be big enough to support the weight of the cistern and the water it contains by spreading load across the roof joists. The platform that the cistern sits on should be covered with 21mm tongue and groove board or moisture-resistant marine-grade plywood. The platform should be at least as big as the base area of the cistern if possible, 150mm larger all the way around. Access to the cistern, once it has been installed, is vital for cleaning, inspection and maintenance. The minimum access allowance will depend on size of the cistern. For cisterns of less than 1,000 litres, 350mm must be allowed to permit access to the float-operated valve before removal and replacement. Inlet requirements for domestic cisterns. Inlet requirements for domestic cisterns. The inlet requirements state that all systems will be fitted with an adjustable water inlet control device. These devices usually float-operated valves that must conform to BS 1212. The British Standard defines 4 types of float-operated valves that are suitable for use in cold water cisterns. Part 1, Portsmouth type, permitted only with a backflow prevention device. Part 2, brass diaphragm type. Part 3, plastic diaphragm type. Part 4, diaphragm equilibrium type, used only on WC cisterns. Figure 5.45 shows a cross-section of a float-operated valve, which can be made of brass. BS1212 Part 2 or plastic BS1212 Part 3. The adjustment screw allows the valve to be set at the correct water level. It is important to note that BS1212 only covers valves up to 54 millimeters in size. Any float-operated valve fitted that exceeds this size must be authorized by one of the following bodies: Water Regulations Advisory Service, Water Fittings and Materials Directory, your local water authority. A low pressure orifice, generally colored red, would be used if the supply pressure was low or the float-operated valve was being fed from another system, say on an indirect cold water system to a WC. The difference between a HP and an LP orifice is simply that the LP orifice has a wide opening to allow greater flow of water. Water outlet requirements for domestic storage systems. Water outlet requirements for domestic storage systems. Outlets from a cistern include indirect cold water distribution pipes and cold feed pipes to hot water storage systems. Figure 5.47 shows the positioning of a cold water distribution and cold feed pipes. It is recommended that the cold water distribution pipe be taken from the bottom of the cistern. This is to prevent the buildup of sediment on the bottom of the tank. Alternatively, the cold water distribution pipe can be located on the side of the cistern. The distance between the cold water distribution outlet and the cold feed to the hot water system should not be less than 25 millimeters. If we look at figure 5.47, it can be seen that the cold water feed for the hot water system is higher than the cold water distribution pipe connection. This is so that in the event of a mains cold water failure, the hot water will run out first, which will prevent any potential scaling situation if any mixing valves, such as showers, bath mixers, or monoblock wash basins mixers, are installed on the system. Prevention of stagnation. Correctly positioned outlet pipes can help prevent stagnation of the water held in the system by ensuring a thorough flow of water. If there is only one outlet fitted, then it must be positioned on the opposite side of the cistern to the float-operated valve. If there are two outlets fitted, they should be positioned on opposite sides of the cistern, with one higher than the other. The higher outlet should be on the opposite side of the cistern from the float-operated valve. This arrangement ensures circulation of the water within the cistern, which in turn helps to prevent stagnation. Materials for domestic cisterns. Health and safety. On no account must any linseed oil-based jointing compounds be used, as this also breaks down the plastic and provides a culture where microbiological growth, such as Legionella pneumophilia, Legionnaire's disease, can occur. Materials for domestic cisterns. Almost all new installations use cisterns made from plastics such as polyethylene, polypropylene, and glass-reinforced plastic GRP. Most cisterns manufactured today are made from polypropylene because this allows lightweight construction, strength, hygiene, resistance to corrosion, flexibility, as they can easily be handled through roof space openings. Cisterns are available either square, rectangular, or circular in shape and are produced in black to prevent the growth of algae. However, because they are flexible, the base of the cistern must be fully supported throughout its entire length and width. Holes for pipe connections should be cut out using a hole saw and not by using a heated section of copper and using it to make a hole in the cistern. Doing the latter alters the molecular structure of the plastic and will result in the cistern cracking. The joint between the cistern wall and fitting should be made using plastic or rubber washers. Galvanized steel cisterns were used for many years. But these were notorious for corrosion. They are still manufactured and can still be used provided the inside of the cistern is protected by the use of a special paint that is registered by the Water Fittings and Materials Directory as safe to use with potable water. Warning and overflow pipes. Simply put, the difference between a warning pipe and an overflow pipe lies in the fact a warning pipe has a smaller diameter than the overflow pipe. It is intended to act as a warning that the float-operated valve is malfunctioned and the cistern is about to overflow. An overflow pipe has a larger diameter than a warning pipe and should be able to carry the excess water that would be present if the inlet valve, float-operated valve, fails completely and lets in the maximum amount of water possible. This should ensure that the inlet valve will never become submerged in water and the cistern will not flood the area in which it is situated. Warning and overflow pipes should run to a point outside of the building that is clearly visible and below the level of the storage cistern. Warning pipes should be situated below the overflow pipe so it is obvious which pipe is which. Overflow and warning pipe requirements for cold water cisterns vary with the storage volume of the cistern installed. Cisterns up to 1,000 litre capacity. Cisterns below 1,000 litre capacity require a single combined warning and overflow pipe. The bottom of the combined warning and overflow pipe should be a minimum of 25 millimeters above the water level of the cistern. Layout features for large-scale storage systems used in multi-story cold water systems. The installation of large-scale cisterns differs somewhat from the cistern you have already been introduced to. Large systems must be installed in accordance with the Water Supply Water Fittings Regulations 1999 and the Scottish Water Bylaws 2004. Regulation 5 states that the water undertaker must be notified before the installation of large cistern begins. And it is important to remember that the correct backflow protection must be present in relation to the fluid category of the contents of the cistern. In this section, we will look at the general requirements of large-scale cisterns. Materials for large-scale cisterns. Large cisterns can be made from several materials and can be either one pipe or sectional. Sectional cisterns are constructed usually on site from 1 meter squared sections, which are bolted together and can be made to suit literally any capacity and tailored to fit any space. Sectional cisterns can be internally or externally flanged and are bolted together with stainless steel bolts. The main materials are described below. For one-piece systems, glass reinforced plastic BSEN 13280 2001, plastic BS 4213 2004, and BSEN 12573 2000. Polypropylene PP, polyethylene PE, polyvinyl chlorine, polyvinyl chloride PVC. For sectional systems, GPR, glass reinforced plastic, steel to BS 1564 1975, with protection against corrosion and subsequent water contamination in the forms of protection with a paint that is listed in the Water Materials and Fittings Directory: glass coated, galvanized, rubber lined, aluminium rubber lined. Overflow and warning pipe requirements of large scale systems. Overflow and warning pipe requirements of large scale systems. Overflows for large systems are quite different from those fitted to systems for domestic purposes. The objective is the same: to warn that the float operated valve is malfunctioning and to remove water that may otherwise damage the premises. However, with large systems, the potential for water wastage and water damage is far greater. Therefore, the layout is different. The overflow warning pipe on large-scale systems must contain a vermin screen to prevent the ingress of insects and vermin. Be capable of draining the maximum inlet flow without compromising the inlet air gap. Contain an air brake before connection to a drain. Not to be of such a length that it will restrict the flow of water, causing the air gap to be compromised. Discharge in a visible, conspicuous position. Discharge in a visible, conspicuous position. The warning pipe invert needs to be located a minimum of 25 millimeters above the maximum water level of the cistern, and the air gap not less than 20 millimeters or twice the internal diameter of the inlet pipe, whichever is greater. The general features of larger systems are as follows. Key terms: actual capacity of a cistern, the maximum volume it could hold when filled to its overflowing level. Nominal capacity of a cistern, the total volume it could hold when filled to the top of the cistern. The overflow warning pipe on the large-scale cistern must contain vermin screen to prevent the ingress of insects and vermin, be capable of draining the maximum inlet flow without compromising the inlet air gap, contain an air brake before connection to a drain, not be of such a length that it will restrict the flow of water, causing the air gap to be compromised. Discharge in a visible, conspicuous position. The warning pipe invert needs to be located a minimum of 25 millimeters above the maximum water level of the cistern, and the air gap not less than 20 millimeters or twice the internal diameter of the inlet pipe, whichever is the greater. The general features of larger cisterns are as follows. Cisterns with an actual capacity of 1,000 litres to 5,000 litres, the discharge level of the inlet device must be positioned at least twice the diameter of the inlet pipe above the top of the flow pipe. The discharge level of the inlet device must be positioned at least twice the diameter of the inlet pipe above the top of the overflow pipe. The overflow pipe invert must be located at least 25 millimeters above the invert of the warning pipe or warning level if an alternative warning device is fitted. The warning pipe invert must be located at least 25 millimeters above the water level in the cistern and must be at least 25 millimeters diameter. Cisterns with an actual capacity greater than 5,000 liters. The discharge level of the inlet device must be positioned at least twice the diameter of the inlet pipe above the top of the overflow pipe. The overflow pipe invert must be located at least 25 millimeters above the invert of the warning pipe or warning level if an alternative warning device is fitted. The warning pipe invert must be located at least 25 millimeters above the water level in the cistern and must be at least 25 millimeters diameter. Alternatively, the warning pipe may be discarded, provided the warning pipe may be discarded. Alternatively, the warning pipe may be discarded provided the water level indicator with an audible or visual alarm is installed that operates when the water level reaches 25 millimeters below the invert of the overflow pipe. In both cases, the size of the overflow pipe will depend on the type of air gap incorporated into the cistern. We will look at air gaps and backflow protection a little later in this unit, and this will depend on the fluid category of the cistern contents. It must be remembered that if type AG air gap fluid category 3 is fitted, the overflow diameter shall be a minimum of twice the inlet diameter. If a type AF air gap fluid category 4 is fitted, the minimum cross-sectional area of the overflow pipe must be throughout its entire length 4 times the cross-sectional area of the inlet pipe. For all systems greater than 1,000 liters, the invert of the overflow must not be less than 50 millimeters above the working level of the cistern. Multiple cistern installations. Interconnection of 2 or more cisterns. Where large quantities of water are required but space is limited, cisterns can be interlinked provided the cisterns are of the same size and capacity. Problems can occur if the cisterns are not linked correctly, especially where the cisterns are to supply drinking water. Stagnation of the water in some parts of the cistern may cause the quantity of water to deteriorate. Cause the quality of water to deteriorate. It should be remembered that the number of cisterns to be linked should be kept to a minimum. Stagnation can be avoided by following some basic rules. Connection must be arranged to encourage the flow of water throughout each cistern. This can be achieved by keeping the cistern volumes to a minimum to ensure rapid turnover of water and thus prevent stagnation. Connecting the cisterns in parallel wherever possible, connecting the inlets and the outlets at opposite ends of the cistern, using delayed action float operated valves to limit stratification. In practice, cisterns in series should be interconnected to allow free movement of water from one cistern to another. They should be connected at the bottom and the middle so that water passes evenly through them. The primary outlet connection should be made on the opposite cistern to the float operated valve to encourage water movement, with the secondary connection made on the cistern with the float operated valve installed. The overflow warning pipe should be fitted onto the same cistern as the float operated valve. Both cisterns must be of the same size and capacity. When connecting 2 or more cisterns, care should be taken to ensure that water movement is regular and even across all cisterns. In this situation, it is a good idea to install float-operated valves on all systems with appropriate service valves as detailed in the DEFRA Guidance to Water Supply Water Fittings Regulations 1999. Service valves should be fitted as close as reasonably practical to float-operated valves. Wherever a float-operated valve is fitted, when an overflow warning pipe must accompany. Where a float-operated valve is fitted, an overflow warning pipe must accompany it. These should terminate in a conspicuous visible position outside the building. On no account should they be coupled together. There should be service gate valves positioned to allow for isolation and maintenance of the systems without interrupting the supply. In figure 5.53 you will see that any two of the four systems can be decommissioned, leaving two in operation. This ensures continuation of supply. Brake systems. Brake systems, often called brake tanks, are used in large cold water installations in order to supply the system with water via a set of boosting pumps where the main supply is insufficient. They provide a break in the supply between the main supply and the installation. This has several advantages over pumping direct from the main supply. Using brake systems ensures that there is no surge on the main supply when the boosting pumps either start or stop. Braking systems ensure that contamination of the mains cold water supply from multi-story installations does not occur. Brake systems ensure that there is sufficient supply for the installation requirements at peak demand. Brake systems safeguard the water supply to others by not drawing large amounts of water from the main supply through the boosting pumps. Brake systems are often used in very tall buildings as intermediate systems on normalized service floors, thus dividing the system into a number of manageable pressure zones. The brake systems provide water to both user outlets and other brake systems higher up, where the water is then boosted to other pressure zones further up the building. As with all system installations, brake systems must be fitted with an appropriate air gap that ensures zero backflow into any part of the system. Frost protection of pipes, fittings and systems. Key point: the thermal envelope is defined as that part of a building that is enclosed within walls, floor and roof, which is thermally insulated in accordance with the requirements of the building regulations. Frost protection of pipes, fittings and systems. You can never fully protect against freezing temperatures. No matter how much insulation there wrap around the pipes and fittings, if the weather gets cold enough, the pipes will freeze. Therefore, we merely delay the freezing process as long as we possibly can by insulating. When we insulate pipes, we are not attempting to keep the cold out. The idea of insulated pipes is to keep the heat that is already there. In other words, we are attempting to retain the heat energy already present in the water for as long as possible. This means insulation is important even under normal conditions, as it maximizes energy efficiency. The greater the thickness of insulation, the longer the heat energy is retained. This is illustrated in figure 5.55, where you will see that for the greater volume of water, i.e. larger pipe sizes, less insulation will be needed. The DEFRA guidance to the Water Supply Water Fittings Regulations 1999 G4.2 states, All cold water fittings located within a building but outside the thermal envelope, or those outside the building, must be protected against damage by freezing. The DEFRA guidance to water supply water fittings regulations 1999 for G4.3 states, if the frost protection provided is insufficient for exceptional freezing conditions, or the premises are left unoccupied without adequate heating, damage and leakage can often be avoided by shutting off the water supply and draining down the system before the onset of freezing. The DEFRA guidance to the water supply water fittings regulations 1999 G4.4 states, where low temperatures persist, installation will only delay the onset of freezing. Its efficiency is dependent upon its thickness and thermal conductivity in relation to the pipe size, the time of exposure, the location, and possibly the wind chill factor. In general, all pipes and fittings that are installed in vulnerable or exposed locations inside or outside a building, such as an unheated cellar or roof space, underventilated spaces, floors, underventilated suspended floors, garages, and outbuildings, must be insulated. Where pipework is installed in a roof space, the pipes should still be insulated even if they are placed below the roof insulation. This is to avoid unnecessary warming by heat from the rooms below. The thickness of the insulation will, as we have already seen, be dependent upon the size of the pipe. Where pipes are located outside the dwelling, the insulation should be to external standards and waterproof. Insulation materials and their effectiveness. Pipework insulation should be of the closed cell type, complying with BS 5422. And installed in accordance with BS 5970. The recommended materials for pipework insulations are rigid phenolic foam, less than 0.020 watts per meter squared Kevlar, watts per meter squared Kelvin. Polyisolanurate foam 0.020 to 0.025 watts per meter squared Kelvin. PVC foam 0.025 to 0.030 watts per meter squared Kelvin. Expanded polystyrene, extruded polystyrene, cross-linked polyethylene foam, and expanded nitrile rubber 0.03 to 0.035 watts per meter squared Kelvin. Expanded synthetic rubber, cellular glass, and standard polyethylene foam 0.035 to 0.040 watts per meter squared Kelvin. The wall thickness of the insulation is shown in Table 5.5. The wall thickness of insulation is shown in Table 5.5. Table 5.5, thermal properties of pipe insulation. External diameter of pipe 15 millimeters. Thermal conductivity of insulation material at 0 degrees Celsius in watts per meter squared Kelvin.